Welcome all to YouTube channel Mechanical Study. Today we will going to start with the fluid machines. We already started with the different subjects which will be helpful for various competitive exams like SSC JEE, RRB JEE, GATE and engineering service exam. So we already started with the different subjects. Today we will going to start with the fluid machines. So here first question for today is, if W is a specific weight of water in Newton per meter cube, A is the cross sectional area of jet in meter square, and V is the velocity of jet in meter per second, the force exerted in Newton by the jet of water impinging normally on a fixed plate. So here consider a case that there is a fixed vertical plate on which jet is striking, which is coming out of a nozzle, and we have to find out the force exerted by the jet in a normal direction to the plate. So this can be written as by using the Newton's second law of motion, that is the rate of change. Whatever the force exerted on a object is nothing but the rate of change of the momentum of a object. So here this can be written as, that is Fn is can be written as mass flow rate, that is F dot, because here we are finding the force exerted per unit second or per unit time. So this can be written as, instead of a mass, here we must find out the mass flow rate. So here there will be initial velocity minus final velocity. This will give us a rate of change of momentum. So here this will be the initial velocity of a jet. So here initial velocity of a jet we are considering as a V, as the jet leaving the nozzle with velocity of V and it's striking the jet and gets deflected through 90 degrees. So final velocity of a jet in the direction of a applied force to on a plate will be 0. So here final velocity will be 0 and initial velocity will be V. So this equations simplifies to F is equal to m dot into V, where m dot is the mass flow rate, and this can be written as rho A V, where rho is the density of a water, A is the area of a jet. So here jet area and the nozzle area are both are same. So here whatever the area of a jet, that is a cross sectional area of a jet, will be equals to pi by 4 d square. This can be written as this d is nothing but the diameter of a nozzle. So this will be mass flow rate can be written as rho into A into V, or this can be written as rho into Q. Here Q is the discharge and discharge is nothing but area into velocity into V. So it again simplify as rho Q square Q V square or rho A V square. So here Fn will be equals to rho A V square. So but this answer is not given in the any of the option above. So here again we'll just multiply and divide our equation with the term G. So it comes out to be rho A V square into G upon G. Here rho into G is nothing but the specific weight, that is W A V square upon G, and this is the option that is given in, so this is the answer that is given in option number D. So here for question number 1, correct option will be option D, that is W A V square upon G, where W is the specific weight, that is nothing but rho into G. A is the area of cross section of a jet, V is the velocity of a jet, and G is the acceleration due to gravity. So here option D will be the right answer. The next question, if mass density is rho, area is A, velocity of jet is V, then the force exerted by a jet of water on a stationary vertical plate in a direction of a jet is given by. So here earlier I have already told you that what is the impact of a jet, that is the by using the Newton's second law of motion, that is whatever the force exerted on an object is nothing but the rate of change of momentum. So this must be equals to m dot into initial velocity minus final velocity. So here final velocity again 0, because the velocity of jet that is in the direction of a applied force to the fixed plate will be 0 after it impinges on the plate. So here it again its value will be, that is Fn will be equals to m dot into P, where m dot is nothing but rho A V into V, that is V square. So here option B will be the right answer, that is F is equal to rho A V square. So here option B will be the right answer. Then question number 3, a 6 cm diameter horizontal stationary water jet having a velocity of 40 meter per second strikes a vertical plate. the force needed to hold the plate if it moves away from the jet at 20 meter per second. Now this is the case where the velocity of a jet is 40 meter per second and velocity of a plate is 20 meter per second. Means this is a case where plate is moving or plate is not stationary. This plate is moving in the direction of applied force of a jet. Here velocity of jet, that is considered as a v, which is 40, and velocity of a plate, that is 20. So here the relative velocity, that is v minus v, will be equals to 20, that is 40 minus 20, this will be the 20. So here this is the velocity with which a jet will strike the plate. So this is the 20 meter per second. So here if you find out the value of force exerted by a jet on a plate, it comes out to be rho a v minus u. This is the velocity with which a jet strikes the plate, and into the, that is initial velocity, that is v minus u. This is velocity at which a jet is striking the plate, to the minus, that is the final velocity, which is 0. As the jet strikes the plate, and once it strikes the plates, it will get diverted through 90 degree. That means its final velocity after striking the plate will become 0. So here again this equation simplifies to, that is Fn is equal to rho a v minus u whole bracket square, where rho is the density, a is the area of cross section, then v is the jet velocity, u is the plate velocity, okay, and v minus u is the relative velocity. So here density is known to us, that is water is 1000, area, that is pi by 4, diameter is 6 centimeter, convert it into a meter. So it is comes out to be, that is 6 into, it is in centimeter, so it is 10 raised to minus 2, that will be in meter or square into v minus u square, that is 40 minus 20 square, that is 20 square. If you solve this, you will get the final answer, that is 1130 Newton, and that is given in option C. So here correct option will be the option C. So here basic difference between the jet which is striking the fixed plate and jet which striking the moving plate is that for a fixed plate, the force exerted will be the F is equal to rho a v square, and for moving plate force is nothing but rho a v minus u square, where this is the velocity at which a jet strikes the fixed plate, and this is the velocity at which jet will strike the moving plate. The next question, that is question number 4. A 75 mm diameter water jet having a velocity of 12 meter per second impinges on a plane smooth plate at an angle of 60 degree to the normal to the plate. The impact on the plate when plate is stationary. So here the question is that again we have to find out the force exerted by jet on a inclined plate. Earlier we have solved a problem for a fixed plate. Now there is a question for the inclined plate. So here this is the inclined plate, and this is the normal force that we have to find out. Okay, so here this is the force that is exerted in a x direction, and this is the in a y direction. Okay, so here the angle is given, that is 60 degree. So this angle is 60 degree, so this is 90 total, this will be the 30 degree. Again if I draw a line parallel to this, so this angle becomes again 90 degree, as this is 60 degree, so this angle becomes 30 degree. So here suppose this is the velocity in x direction, that is v. So here if this is v, then this value, as we apply a Pythagoras theorem for this triangle ABC, then this becomes v sin theta, and this becomes v cos theta. That is, this will be the velocity in a normal direction, and this is the velocity that is parallel to the plate, and this is the velocity v, which is in a direction x direction. Okay, so basically here the velocity of a jet which is normal to the plate, this will be v sin theta. So here this is the initial velocity with which jet strikes the inclined plate. So here if you put this or if you find out the value of Fn, so it is comes out to be, as you all know, that the Fx is nothing but rho a v square, rho a v square. Okay, so here in earlier case we already seen this condition. So here the velocity of a jet, that is in the normal direction, that is v sine theta. So instead of that, there will be Fn will be equals to rho a v square into sine theta, where theta in this case will be the, it is angle which is 30 degree, that is which already here this is not the exact angle, that is here that given angle is 60 degree. There is a smooth plate at an angle of 60 degree to the normal to the plate. So this is not the actual theta angle. The angle that we need is, that is angle form over here. Okay, this is the angle theta. We don't need this angle, we need this angle which is theta. Okay, so here this theta angle is 30 degree. So here the Fn will be equals to, that is rho is nothing but 1000, area is nothing but pi by 4 d square, that is 75 mm square converted into meter, then v square which is the velocity, that is 12 square into sine 30. If you put in the equation, you will get the final answer, that is equals to 317.925, that is approximately equals to 317.93 Newton. So your option C will be the right answer. The next question, that is question number 5. A nozzle at the end of an 80 mm hose pipe produces a jet 40 mm in a diameter. When it is discharging the water 1200 liter per minute, the force on the joint at the base of a nozzle will be. So here the question is that how to find out the force on the joint at the base of a nozzle will be. So here we can say a diagram, that is there is a hose pipe. Okay, so this is a hose pipe, so its diameter is 80 mm and it produces a jet with a 40 mm diameter, means the whatever the jet produce having a diameter of 40 mm, when it discharges, that is the discharge is nothing but 1200 liter per minute. So you have to convert into meter cube per second. So here to convert liter into meter cube, so it is multiplied with the 10 raised to minus 3, and to convert meter into second, it is divided with the 60. So you will get the discharge, that is equals to 0.02 meter cube per second, that is 0.02 meter cube per second. So with this, as the discharge will remains constant, that is you apply continuity equation, that is a1 v1 will be equals to a2 v2, means discharge will be remains constant, that is at the hose side as well as at the nozzle side. So only change is that there will be, as the area changes, its velocity will also changes. So here v1 is first find out with the help of q by a1, that is the area of a hose, and v2 is the q upon a2. So we'll get the v1, that is 3.9 and v2 15.9. so here the final, that is force at the joint, that H will be equals to, comes out to be, that is rho a v square, or it can be written as rho into q, that is a discharge, into final velocity minus initial velocity. It is comes out to be 1000 into 0.02 into 15.9 minus 3.9. so it is comes out to be a value of 240 newtons. So approximately, as its answer comes out to be 240 newtons. So here option D will be the right answer for the question. The next question, force exerted by jet of water impinging on a moving plate is. So here plate is also moving along with the, that is there, as there is a impact of a jet takes place. So here earlier I have told you that that formula is nothing but, that is Fx is equal to rho a, and as plate is moving, so here jet will strike the plate with the velocity v minus u. This will be relative velocity, that is v minus u. So here rho is the density, a is the area of the jet, v is the velocity of a jet, u is the velocity of a plate. But in question, that is an option, this answer is not given. So here just we have to again simply that multiply divide with the term g, so we will get the final answer, that is in terms of G. So here the final answer will be equal to, that is option A, that is W upon G into area into V minus U whole bracket square. So here option A will be the right answer. The next question, this a series of normal flat vanes are mounted on a periphery of a wheel. The vane speed being V. For maximum efficiency, the speed of liquid jet striking the vanes should be. So here consider a case that there is a runner over which there are number of flat plates, and there is a, suppose there is a jet of water that is striking the nose, that is a jet which is striking the this plate. So here this, suppose this is the velocity u with which blades are moving, and this is the velocity of a jet. So here relation between the, for maximum efficiency the relation is nothing but v u is equal to v by 2, that is the runner speed will be equal to half the jet speed. So here the correct answer will be, as the jet striking the, that is in this case this will be equals to, just a minute, here there is given the vane speed is being v, so here vane speed is given, that is v. Okay, so that is the this vane, okay, vane or blade speed is given here v. So here this is v. So here in this case, suppose jet is striking with the velocity of u. Okay, so earlier I have told you the reverse case, that is here as per the given condition, that is v is the velocity of a runner. Okay, velocity of a runner or a blade or a vane. So here v is the speed, suppose u is the speed at which it is striking the vane. So here for maximum efficiency, the this v speed, that is the speed of a runner blades, this u must be equals to u by 2, that means u will be equals to twice v. That means a jet velocity will be equals to twice the vane velocity for maximum efficiency, for efficiency to be maximum. So here option D will be the right answer. The next question, so we'll start with the hydraulic turbines. Basically there are three types of turbines that we have to see. That is the impulse turbine. In that first of all we will see about the Pelton wheel, and secondly basically there are two types of turbine, that is impulse and reaction turbine. And in that also there is a impulse turbine, that is a Pelton wheel, and reaction turbine, there are two types of reaction turbine, that is first is the nothing but the Francis turbine, and second is nothing but the propeller or a modified version of that is the Kaplan turbine. Okay, so we'll see the questions on hydraulic turbines. Okay, so basically hydraulic turbines are installed on a hydroelectric power plant, basically for the electricity generation. So here first question, the purpose of surge tank in a pipeline is to. So here I will just draw a diagram of a hydroelectric power plant. Basically in a hydroelectric power plant there will be a dam, which is act as a reservoir where plenty of or abundant amount of water will be present. And from that tank there will be one long diameter pipe, long length as well as diameter pipe, which is extended up to turbine, and in turbine there will be a number of vanes provided on the runner. As in case of a impulse turbine there will be a nozzle at the outlet of this penstock. So basically on a penstock end, that is before the nozzle, there will be one tank which is called as a surge tank, which behaves like an accumulator. So here which just holds the plenty of water that is coming out from the dam. So okay, so basically surge tank is behaves like a accumulator where we can store plenty of water, and then it is supplied to the runner whenever it required. Okay, so basically a surge tank is nothing but the, so options are remove friction, prevent turbulence in the flow, prevent flow loss, relieve pressure due to water hammer. So basically option D will be the right answer. Its function is to relieve pressure, as there is a case of water hammering means what, Suddenly when we stop the water flow, that means as per the requirement on the turbine side, we may shut down or we may regulate the flow of water to the turbine blades. Okay, so once we regulate the flow of water to the turbine blades, there may be chances that the generation of pressure waves because of water hammer. Water hammer means what? We are suddenly closing the flow of water from the penstock to the turbine, which enables the tremendous rise in pressure in the penstock. So in order to prevent this, a surge tank is provided towards the end of a penstock, so that it will behave like an accumulator. The whatever the water hammering effect that can be nullify with the help of a surge tank, so that the excess water will be supplied to the surge tank, and again that can be used further whenever there is a opening of a that is a wall that will allow the flow of water to the turbine blades. Okay, so here option D will be the right answer. The next question, the valve closure is said to be gradual if time required for to close the valve is. So here number of options are given. So here L is the given thing is that the L is the length of a pipe and C is the velocity of a pressure wave. So here correct answer will be the option D, that is the for a gradual closing or a sudden closing, the time is nothing but should be greater than twice of L by C. That is L is nothing but the length of a pipe and C is the velocity of a pressure wave that is produced due to water hammering. So their option C will be the option D will be the right answer for the given question. The next question, the magnitude of water hammer in a flow of a liquid through the pipe does not depend upon. So here number of options given, that is the length of a pipe. So it depends upon the length of a pipe. The next, elastic properties of a pipe material, also it depends upon that also. C is the temperature of a liquid. So it is not depend upon the temperature of a liquid. So it is irrespective of the temperature of a liquid. The magnitude of water hammer in the flow of liquid, it does not depend upon the temperature, but it depends upon the number of properties like gradual opening or sudden closure or opening of a wall in a pipe, then some of the elastic properties of a pipe material, then what is the length of a pipe. Okay, then time of wall closure, that is whether wall is closing suddenly or whether that is wall is closing slowly. So these are the things on which a water hammering effect will be depend. So here option C will be the right answer. The next question, this is question number 11. Water hammer is developed in, so without any doubt it is developed in penstock. Earlier I have told you the and also draw a hydroelectric power plant diagram, that is a dam is there, then penstock, through the penstock water will flow to the through the nozzle. If there is impulse turbine, there will be a nozzle. If there is no impulse turbine, there will be no nozzle. Okay, so in case of reaction turbine, there is no necessity of any nozzle. So here option A will be the right answer. The next question, the most probable value of speed ratio of Kaplan turbine is. So here speed ratio, that is nothing but Ku. Okay, so this Ku is generally equals to 2. Okay, so this will gives us a value between the that is the velocity of a blade and the velocity of a blade and the velocity of a jet, that is V. Okay, so this will use as a velocity of a V, and this is the V is the velocity of a jet leaving the nozzle. Okay, so here this relation between these two gives us about the that is the speed ratio. There is another term, that is flow ratio, which will gives us a velocity of flow velocity, relation between flow velocity and the velocity of jet leaving the nozzle. So this is the Kf is the flow ratio and Ku is the speed ratio. So speed ratio in case of a Kaplan turbine is 2.0. Basically, a Kaplan turbine is a modified version of a propeller turbine. It is a type of a reaction turbine in which a propeller turbine basically it is a modification of a propeller turbine, because in earlier cases the propeller turbine was invented, and this type of turbines are having there are two types of blades in case of a reaction turbine. This is one of the type of axial flow turbine, that is flow is axial to the, or flow is along the axis of a turbine. And here in this case there are two types of blades, that is a first one is a guide blades, which are adjustable one, and there is a second, that is moving blades. But in case of a propeller turbine we cannot adjust moving blade, but in case of a Kaplan turbine we can adjust the moving blade. So this is the basic difference between propeller and Kaplan turbine. And in case of a Kaplan turbine the speed ratio is approximately equals to 2. Okay, so this is the value, that is Ku is equal to U, that is the blade velocity, upon square root of 2gh. So this blade velocity can be found out with the help of formula pi d n by 60. Okay, so it is its value for the impulse turbine, again it is different, for reaction turbine and again it is different. The next question, that is question number 13. Runaway speed of a Pelton wheel means. So basically runaway speed of a Pelton wheel, options are full load speed, no load speed with no governor, then full load speed with governor mechanism. So here runaway speed is the speed and there will be no load and there will be a case of a no governor, means option C will be the right answer. The next question, speed ratio of a Pelton wheel varies from. So here for a Pelton wheel, again I have told you the speed ratio, that is gives a relation between the velocity of a jet and velocity of a jet that is coming out of the nozzle and the blade velocity. So it is ranges between the speed ratio for Pelton wheel, it is ranges between 0.45 to 0.45. So it is some of the books also it is given in the range 0.43 to 0.47. So here either this, that is 0.45 to 0.5 or 0.43 to 0.47, this can be taken as a right answer for a Pelton wheel, that is speed ratio. The next question, a draft tube is used with. So basically a draft tube is used at the end of a reaction turbine, means there will be some reaction turbine. Okay, so here draft tube will be used. Okay, suppose there is a inward flow reaction turbine, in that there will be guide vanes, then there will be some of the running that is a moving blades, and there will be axial flow, and there will be one gradually increasing diameter tube which is called as draft tube, that is at the end of the of a Francis or a Kaplan turbine. So here the function of draft tube, that is a gradually increasing cross section it is having, and its function is to have a pressure well below than the atmospheric pressure at the outlet of a turbine. So here we can see the case, that is there will be pressure at below than the atmospheric pressure, and there will be here there will be a tail side of a Francis or Kaplan turbine. Okay, so this will be the tail race where water will be delivered to the nearby river on the dam. Okay, so basically a draft tube that is installed for the reaction turbine, that is in the case of either in a Francis turbine or in a case of a Kaplan turbine. Then that is, so their option B will be the right answer, that is draft tube is used with the reaction turbine. The next question, which of the following needs maximum head? Options are Kaplan turbine, Pelton turbine, Francis turbine and reaction turbine. So without any doubt a Pelton turbine needs a higher head. So here option B will be the right answer. Basically in earlier cases, that is when there was a hydroelectric power plants invented, and the turbines that is used are the Pelton wheels, and basically this Francis or a Kaplan turbines are come into picture later words. That is Kaplan's turbines are basically can be installed with the lower heads also, with a lower head, that is up to 30 meter height, also we can install a Kaplan turbines. Okay, so basically for higher heads and with low specific speed, so this is the specific speed. So basically ns is the specific speed, and the next is nothing but the here is that the head, that is for a higher head and lower specific speed we can use a Pelton turbine. Okay, then similarly for a higher specific speed and lower head we can use a Kaplan turbine, and for medium and speed and medium head we can use a Francis turbine. The next question number 17, the speed of govern statement is given, that is the speed of govern water turbine will remain constant irrespective of the load. So here it is a correct answer, that is we need to maintain the speed constant. The function of a governor is to maintain the speed constant irrespective of the load on the turbine. Okay, so basically the turbine or a governor ensures that the speed of a turbine is constant. Means suppose the speed of a turbine is 3000 rpm, then it needs to be constant irrespective of the load on the turbine. So basically its function is to maintain the speed of a turbine constant irrespective of the load. Then statement second is the in governing the water supply is regulated to maintain the speed constant. Again it is a true statement. So both statements are true. The next question, if the head on the turbine is more than 300 meter, the type of turbine used should be. So without any doubt, for heads which is greater than 250 mm, say heads that is greater than 250 mm, sorry 250 meter, sorry 250 meter, we can use a simply a Pelton wheel can be used for a higher head. Okay, so here option C will be the right answer. So here we can see the range of a turbines. Okay, so Kaplan turbine we can use for a head of a 10 to 30 meter, that is for a high discharge. Okay, that is specific speed will be more in case of a Kaplan turbine, and there will be a high discharge and head will be the lower. So for lower head we can install Kaplan turbine, and basically Kaplan turbine having a number of blades that is very less as compared to that is as compared to turbines like Francis and Pelton wheel. Then for a propeller turbine, again couple basic difference between the Kaplan and propeller turbine is that in case of a Kaplan turbine the moving blades are adjustable, but in case of a propeller turbine moving blades are not adjustable. So this is the basic difference between the two turbines, but both are the axial flow turbines. Then propeller turbines, then next is the Francis turbine that will be used for 30 to 50 meter. Nowadays a mixed flow Francis turbine, that is a combination of radial and axial flow turbines are basically Francis turbine, that is used in the hydraulic power plants. And basically Francis turbine is one of the simplest type of a radial flow reaction turbine. Then Pelton wheel, this is used for a head of a head greater than 300 meter or 250 or above than that. Pelton wheel can be used with lower specific speed. Okay, so this is the all for the different types of turbine with heads and specific speed. Then question number 19, that is the main characteristics curve of a turbine means. So basically there are two types of curves. First is the mains, and second is the that is operating. So basically mains characteristics curves are plot with a constant head, that is maintaining the head constant, and operating characteristics curve are plot with the maintaining the speed constant. So irrespective of the load, whenever we have to plot operating characteristics curve, we need to maintain a speed constant, and for mains characteristics curves we have to maintain the head constant. So here main characteristic curve of a turbine means curves at constant speed. So it is not true, because it is the curves that is drawn for with a constant speed that are called as operating characteristics curve. The next question, curves at constant efficiency, so it is called as IC efficiency curve. Okay, that is curves with constant efficiency, and curves with constant head, that is measured with the help of a, so that is called as a main characteristics curve. So option C will be the right answer. The next question, that is impulse turbines works on the principle of, so without any doubt it works on the principle of that is Newton's second law of motion, that is F is equal to force is equal to rate of change of momentum, that is M is equal to rate of change of momentum. This M into V is nothing but the momentum. Okay, so that means that whatever the change in momentum of any body will be in the direction of the applied force. The next question, that is question number 21. Which of the following turbines is suitable for specific speed ranging from 300 to 1000 and heads below 30 meter? Okay, so this is a case of a lower head with higher specific speed. So higher specific speed, without any doubt we can use a Kaplan turbine. So here option B will be the right answer for higher specific speed, that is ranges between 300 to 1000. Okay, or above than that also we can use a Francis turbine with a low head, that is 30 meter. Okay, above than 30 meter up to 50 meter we can use a Francis turbine, and a head that is above than 250 meter we can use a Pelton wheel. Similarly, specific speed in the range 10 to 35 or 10 to 35 we can use Pelton wheel, then that is type of impulse turbine. Then for a specific speed in the range 60 to 300 we can use Francis turbine. The next question, that is question number 22. So this will be the last question for today. If the number of jets in a Pelton wheel installation are n, okay, so number of jets are n, then specific speed is proportional to, so here if there are n number of jets, okay, if there are n number of jets, okay, so then the specific speed ns will be equals to, so the relation between them is nothing but 1/2 of n, that is the number of jets. So specific speed of a turbine will be the square root of number of jets. Okay, so this will be the correct answer. So option B will be the right one. Okay, so this will be all for today. I hope you all enjoy today's lecture. So do like and subscribe to our channel, share with your friends, and also continue with us the different subject series, as today we started with the fluid mechanics subject. So in upcoming days we'll start with the we start with the various mechanical engineering subjects like SOM, TOM, machine design, and other subjects. So do like and subscribe to our channel.